All right, so good morning, everyone. Today we'll be talking about single-phase circuit as part of our electrical technology course. So from the title of the chapter, the first thing that should come into your mind is what is single phase, okay? Which actually implies there may be some multi-phase, right? Whenever I'm saying single phase, that actually indicates that there should be some multi-phase. Yes, there is actually, and that's why we start with single phase, and in the later lectures, in the later chapters, we move on to three-phase circuits. So most common phase that we have in our domestic life, day-to-day life, in our houses, the power supplies that we have, they're all single phase. What we mean by that we'll see in the later slides. We'll go obviously deeper into that. On the other hand, three-phase circuit, we don't really encounter three-phase circuit in day-to-day life. Three-phase circuits are mostly applicable or used in the industrial setup because of power requirement and the devices they use in the industry. Those are made for three-phase circuits. Usually that is the case, but in domestic life, we don't use single, multi-phase or three-phase circuit. All right, so the first thing first, single-phase circuit. What can you expect from this lecture? At the end of the lecture, the students are expected to be familiar with single-phase AC circuit. The whole lecture is supposed to make you familiar with what is single-phase circuit. They should gain understanding of the behavior of various AC components. For example, impedance of resistance, inductance, or capacitance in a single-phase circuit. They should gain a clear understanding of the relative phases within the single-phase AC circuit, how the phases for the current and the voltage differs in various circuit configurations. And at the end, they should be able to analyze a single-phase circuit using phasor representation. All right, so you have already got some idea about phasors, right? Whenever we are dealing with multiple AC signals of the same frequency, phasor is there to help us. Phasor is there to make our life really easy, and we can represent any signal in terms of phasor as long as they have the same frequency. So since we will be dealing with single-phase circuit, and for AC, the basic components, in addition to resistance, of course in DC you are already familiar with resistances, but whenever you are dealing with AC, there are two other basic components, which is inductance and capacitance. And all the analysis we'll be doing in this chapter and obviously throughout the course will be in phasor domain, which we covered in the last lecture, and you already know how we can represent any voltage or any AC signal in terms of phasor. The first thing, I want to familiarize you with how we can represent an inductor or a capacitor in AC. In other words, what would be their impedance? For example, for resistance, you already know what is the resistance. That is the value right away. That is the resistance it exhibits in response to any AC. Doesn't matter what frequency. But what about inductors or capacitors? If I give you an inductor, the first thing you know is the inductance of that inductor, right? Which is some Henry. That is the unit for inductors, for inductance rather. In terms of capacitors, if I give you a capacitor, first thing you know is the value of the capacitance. It's written with some codes, it's written on the capacitor. But what kind of impedance does it exhibit if you connect it to the AC? Or in other words, if you connect that inductor or that capacitor in the AC circuit, what kind of current can you expect? So that is the question. So again, go back to that basic Ohm's law. I is equal to V divided by R. In case of AC, this R becomes Z, and we call that impedance. And V on the numerator, it is a phasor. Z in the denominator, it becomes a phasor, and the resultant I becomes a phasor. Okay, so why Z is a phasor we'll see in a bit. So basically first thing we'll look into the impedances of inductors and capacitors in an AC circuit. All right, so let me bring up part of the module just to show you how we derive the impedance for inductance. First thing, I want you to concentrate on this relationship here. This is the voltage across an inductor if the current through the inductor is IT. So for an inductor, assume the current through it is IT, which is equal to Im cos of omega t plus phi. Okay, phi is the phase angle. So the voltage across the resistor in response to that current would be L di by dt. So basically now we are trying to find out the voltage current relationship through an inductor. So basically what is the relationship between the current that is flowing through the inductor versus the voltage across that inductor. Okay? So this is the basic relationship. It comes from electromagnetism. If you go to the basics of inductor, you'll see how you can get this relationship. But for now, this is beyond the scope of this course, but I'm sure it will be covered in some other courses, electrical components or something. So for now, just know that the Vt, which is the voltage across an inductor, is related to the current through it through this relationship, L di by dt. So what is di by dt? The rate of change of current through the inductor. Okay, and L is the inductance in Henry. You know that, right? The unit for inductance is Henry. So if you go on and replace substitute Im cos of omega t plus phi in place of I, and you get this. You go on with the time derivation, you will get this. Okay, so now you can convert this into a function of cos, and you get this at the end. So this is the Vt across the inductance, and that is the It through the inductance. Now you are in the situation to basically know what is the impedance of an inductor, because you know the current through the inductor, you know the voltage across the inductor. So how can you get the impedance, or which is equivalent to resistance? Can you tell me how? Go back to the Ohm's law. I is equal to V by R. In other words, R is equal to V by I. So you have V, which is this. You have I. Can you derive the impedance? Okay, so you can. Okay, first thing, the easiest way would be to convert this into phasor form, and you know the impedance. Okay, so I'll do it on the board. So the first relationship that we have for the current is It is equal to Im cos of omega t plus phi. Okay, so that is the It. So in phasor domain, this It we can write as I is equal to Im with an angle of phi, right? So that is the current in phasor domain. What about the voltage across the inductor? Vt is equal to omega L Im cos of omega t plus phi plus 90 degrees, right? The first thing actually is pretty obvious to you right away, that it's leading by 90 degrees. Look at the phase. Both of them are in the cos, and right away you can tell that it's leading. I mean the phase relationship, because there's a 90 degrees plus 90 degrees, so you can tell right away that it's leading the voltage is leading the current by 90 degrees. Okay, let's go for the impedance. Let's try to, okay, in phasor domain, this would be, we can write this as V is equal to V, sorry. omega L Im with an angle of what? Tell me. Phi plus 90 degrees, right? Great. So now the impedance Z is equal to, let's call it VL. Voltage across the inductor and this, let's call it IL. The current through the inductor. Okay, L is for the inductor. All right, so Z is equal to V divided by VL divided by what? IL. Thank you. IL. Okay, so if you do this math, what do we get? 1 over, I'm sorry. We get, so basically Im cancels out and get omega L with an angle of 90 degrees. How great is that? We have the inductance, the impedance for the inductance, which is omega L, and it has an angle of 90 degrees, positive angle. So if I want to write this in a rectangular form, can you tell me what that would be in rectangular form? Remember, the easiest way to do rectangular form is to do it graphically. So you have this omega L, and the angle is positive 90 degrees. So right here, this is real axis, this is imaginary axis. So you have a vector that runs from the origin to omega L. So can you now tell me what would be the impedance in rectangular form, the impedance for the inductor? It's J omega L, right? Because there is no real part. We just only have the imaginary part. That means J omega L. Is that okay? Great. So now you know that the impedance, so we call this impedance in case of AC, we call this impedance. It's no longer resistance. It's similar to resistance in DC. So impedance, one of the first thing you should notice, impedance itself is a phasor. The vector like, or, you know, sort of like vector, but it's not a vector, it's a phasor. Okay? Right. Now let's have a look what is the impedance of a capacitor. Now we know the impedance of an inductor is a purely what? It's a pure imaginary number without any real part. And the impedance of a resistance is a pure real number without any imaginary part. So let's have a look at the impedance of the capacitor. So there it is. We have a very similar relationship for the case of a capacitor as we had. So we start with VT. In case of inductors, we started with Im, the current through the inductor. There is a reason. The reason is this, the relationship. Because for the case of inductor, the relationship is based on di by dt. But for the case of capacitor, the relationship, voltage current relationship, is based on dV by dt. Okay, it's very symmetric and very complementary. One deals with the current, the other one deals with the voltage. So there is a symmetry, which is beautiful. Anyway, so we start with VT. Let's say the voltage across the capacitor is this. Okay, the current through the capacitor is I equal to C dV by dt. Why? That this relationship comes from electromagnetism, basic electrical components. If you want an explanation to this, you have to go to that. But for now, just know that this is the relationship. In case of, remember, in case of inductance, the relationship was Vt was L di by dt. But in case of capacitor, I is equal to C dV by dt. Rate of change of voltage with capacitor. So if you carry on, and at the end you will see, you will end up in a very similar relationship. Only the only difference is you carry on in the same way we did for inductors. And at the end, what you get is ZC, which is the impedance because of the capacitor, would be equal to 1 over j omega c. So for inductor, it was j omega L. And for the capacitor, you proceed there, just there's a couple of steps there. You proceed same way, and you end up with this relationship. So the impedance because of a capacitor is what? 1 over j omega c. And the impedance due to an inductor, what is the impedance? J omega L. Perfect. All right, so let's move on to actually deal with single phase circuits. All right, so here are some very basic examples of how you might have multi-phase circuits. The first one that you can see is the single phase circuit. So it basically has a single source of AC, and there's a very basic series circuit. You can see the R, L, and C are connected in series. And you are already familiar with the concept of ground, are you not? You are. So you know that whenever there's ground, all the grounds are basically short circuit. All right, you might have this kind of configuration as well. What is this? It's two-phase circuit. So you basically have two voltage sources. Only difference between the voltage sources are the angles of those voltage sources. For example, this one, it has 0 degrees phase angle, and this one might have 90 degrees. But in reality, you'll hardly encounter this kind of two-phase circuit. Mostly you will see this kind of three-phase circuit in the industrial setup. So what do you have in three-phase circuit? First of all, of course, you have three different voltage sources, AC voltage sources, and they could be connected in two different ways, but we'll get into those three-phase circuit in later chapters. But for now, all you can see, I mean, the basic thing that you can see about this, it has three separate voltage sources, and each of the voltage sources, the phase of each of these voltage sources differ from each other by how many degrees? 120 degrees. Good. So it's a three-phase, four-wire system. This is a two-phase, three-wire system. Okay, do you spot the difference? Of course we did already. All right, so let's have a look. On the left-hand side, we have a very basic single-phase circuit with an impedance ZL. L actually usually implies impedance. And on the right-hand side, we have a two-phase circuit. It's actually single-phase, but two-wire system. Two-wire system and this is a three-wire system or three-wire type, and this is called two-wire type, this kind of connection. So two identical sources. All right, so this is just a recap. You're already familiar with these. What are the passive elements and what are the active elements? We'll just skip through this. Resistance, reactance, and impedance. So we have already started talking about impedance. I think this is the first chapter that we started talking about impedance in this course. So what is an impedance? Impedance Z is a comprehensive expression of any and all forms of opposition to electron flow, including both resistance and reactance. So basically, it's very similar to resistance. What does resistances do? What do resistances do? The resistances, they resist the flow of current, right? Infinite resistance means open circuit, and zero resistance means closed circuit. There is no resistance. Same thing, impedance. Impedance actually resists the flow of current in an AC circuit. So it has two components. Any impedance will have two components, the real part and the imaginary part. The voltage drop always lags current by 90 degrees. The voltage drop always lags current by 90 degrees. It's not really accurate, the statement, but it depends on the on the impedance, overall impedance. But let's ignore this for now. Resistance R is essentially friction against the motion of electrons. That's very basic physics. Voltage drop and current are always in phase. In case of resistance, the voltage drop and the current is always in phase. Okay? Why is that? If you consider a voltage source, let's consider a voltage source which in phasor form V0, let's say. Okay? And let's consider the impedance of the resistance. Can you tell me what would be the impedance of a resistance? The impedance of a resistance would be just R. Just R. That is the impedance. If there is just a resistance, R is the impedance. And what is it? It's a real number. It's not a complex number anymore. Of course, you can't say that it is a complex number with the imaginary part as 0. Okay, so what happens if you do this division? The first thing is, of course, the magnitude, the resultant phasor. The result is a phasor, of course. The resultant phasor has a magnitude of V divided by R. What happens to the angle? Does anything happen to the angle? Nothing happens to the angle. So the angle is same. So in other words, the division gives you the current, right? So the current will have the same phase as the voltage. The current is going to have same phase as the voltage itself. But if you try with the, let's say, inductor and see what happens. Let's try with an inductor, because we already know the impedance of an inductor, right? So we can try it right away. Very simple. Because it's a division that we want to do, the current is equal to voltage divided by the impedance. So it's a division. So how do we do it? Do we do it in polar form or in rectangular form? Polar form is the easiest way. Of course, we can do it in rectangular form as well. There's no problem, but it becomes difficult. Okay, let's write down the voltage. V with an angle of 0. And omega L, sorry. Remember, it was J omega L, right? ZL, it was equal to J omega L. So in polar form, it's omega L with an angle of positive 90 degrees. Okay? And that is going to be IL, sorry. So you can see that IM lags. So the resultant is going to be some IM. Let's say this is IM. And the angle is going to be negative 90 degrees. So you can see, that's how we started actually. So we can say, in case of inductor, the voltage across the inductor leads the current through the inductor by 90 degrees, or in other words, the current through the inductor lags the voltage across it by 90 degrees. Because you can see, this is the voltage across that inductor, whatever inductor that we are considering, and this is the current through that inductor. So see the relationship? The voltage has 0 angle and the current has negative 90 degrees. Right? So it's very obvious. So if you do the same thing with capacitor, you're going to end up with a very similar relationship, but it's just opposite. So you'll probably find, not probably, you will find the voltage, if you consider the voltage as 0, IM with an angle, the current through the capacitor would be positive 90 degrees. So the current through the capacitor leads the voltage across it by how many degrees? 90 degrees. It's very similar, very symmetrical, complementary to each other, this capacitance and the inductors. All right. Okay, so whenever you have both real part and imaginary part, it's typically called impedance. And this imaginary part, you already realize that it comes from capacitors or inductors. Okay? And this real part is obviously from resistances and nowhere else, just pure and simple resistance. the reactance X. So this part, the imaginary part, is called reactance. Okay, if you want to refer to just the imaginary part, which is coming from the inductor or capacitor, we call it reactance. The reactance X is essentially inertia against the motion of the electrons. So this comes from pure physics. So voltage drop always leads current by 90 degrees. It depends on whether it's inductive or capacitive. So this is not accurate whenever I'm saying this. Let's ignore this for now. All right, time domain and phasor domain. So we talked about these things in the last lecture. You have this voltage waveform, and you can represent this as a phasor. Very simple. Sinusoids, phasor transformation. Can you convert this? Can you represent this into phasor? For example, let's consider this one. This one would be Vm phi. Remember, cosine. You express the waveform as a function of cos, and you take the angle, pure and simple, that is the angle of that phasor. For example, for this one, you convert this into cos, and you take the angle, that becomes the angle of that phasor. This one is already in cos. So, for example, this one, the phasor would be, the amplitude for the phasor is Im, and the angle for the phasor is phi. Same thing with this one. You have to convert this first into cos, and this becomes the angle of the phasor. All right. So these are the solutions. Okay. Comparison, sinusoid phasor transformation. Okay, what do we have? So this is in time domain, this is in phasor domain. Same thing. So we have this waveform, and we have this phasor corresponding to that waveform. Is the instantaneous or time domain representation time dependent? Is always real with no complex numbers. Of course, time domain is something physical we can understand right away. But the phasor domain is not entirely intuitive. It's not comprehensible. We cannot really relate this to physical world. But of course, it's really useful when we want to analyze AC circuits. Okay, so this is the frequency or phasor domain representation. So this is, sometimes it's called frequency domain representation as well. No time dependent, is generally complex. All right, examples. Transform these sinusoids to phasors. So we have the current and the voltage in time domain. We want to get the phasor representations for these two signals. Can we do that? Right away, of course we can. For example, the first one. Of course, one thing you should notice is they have different omegas. They really have different frequencies, angular frequencies. First one is 50, the second one is 30. So of course, you cannot have these two signals in real life in one analysis. You can't have that. Of course, you can have that, but in that case, phasor representation is not going to work. For the voltages or the signals to be represented as phasor, remember one of the criteria, all the signals need to be with the same frequency. So, but this is just an example. Let's move on. Let's see how it's done. Okay, so the first one is obviously is I, which is 6. Amplitude is 6, and the angle is negative 40 degrees. The second one, obviously, you have to convert this to cos wave, and then that's how you find out. So how do you convert? Can you convert this from the diagram that I gave you, or you just remember the trigonometric identities to make this conversion? So if you do this, negative sine A is equal to this. So negative sine of 30t plus 50 degrees would be, you just add 90 degrees, and it becomes positive cos. So there you go. The angle becomes 140 degrees, and the magnitude is 4. Okay, let's move on. Okay, what do we have here? So some examples for Laplace transform, which will not be using Laplace transform in this chapter, but it's good to know. Laplace transform. Have you had this in maths? Okay, so you're already familiar with the Laplace transform. Laplace transform is something, it's in S domain or in sort of like in frequency domain, complex frequency domain. So the thing that we have, the waveform that we express in the as a function of sine or cos, what domain are they in? They're in time domain as a function of time. And we can relate to the changes. Whenever it's in time domain, we actually can see the changes, or we can feel, or we can relate that change to the real world. But whenever something is in, let's say in phasor domain, we cannot really relate it to the physical world. Same thing in the S domain or complex frequency domain. We cannot really, whenever we represent something in S domain, it doesn't really tell us much about its relationship with the real world. But why do we need this? It makes our life really easy, like exactly as phasor does. How does phasor help us? It makes the analysis really easy for us in case of AC circuits. Okay. Same thing with Laplace domain representations. It really helps us with, especially when we do these kind of time derivative or integrals or these kind of calculus operations. So if we resort to this Laplace transform, the whole operations becomes really easy. So here are some relationships, for example, for R. Okay, let's go to the first one. We have Y, which is represented in time domain. In frequency domain, it would be represented like this. So the letter usually becomes capital letter, and whenever it's in time domain, we usually use, tilted lowercase letter. That's the convention. So Y dot is, what is Y dot? Whenever you have a prime, sorry, not dot, it's prime, is time derivative, ddt. So if it's time domain, in time domain you do time derivative. In Laplace domain, you see, it becomes so easy. So this is the ys, you multiply with s and minus y0. Okay? Y0 means you put the value of s equal to 0 and you evaluate, so that gives you a value. And so basically it gives you the value of y at time t equal to 0. So this is basically time domain representation, this part. And so on and so forth. For y double prime, which is a double derivative of y in time domain, you can use this relationship in frequency in S domain. So you see, this kind of relationship is really easy for you to calculate. That's why we actually resort to Laplace transformation in electrical circuits. All right, so let's have a look at this table. We have element R in time domain. This is the voltage across R, but in phasor domain, this is the voltage across R. Very simple for R. Okay. What about inductance? We have the L, the letter that indicates inductance. In time domain, we already know this relationship, right? Vt is equal to L di by dt, and in frequency domain or in phasor domain, it's this one. We already know this. What about capacitor? Same thing, similar thing. You have the time domain representation, basically the relationship between the current and the voltage, and in phasor domain, it becomes this. All right, the summary of L, R, and C circuits. So for resistors, wait. So that is the relationship for resistor. Okay. See, voltage, let's say this is the complex plane, and you have a voltage. The voltage, obviously, it has an angle. The voltage, what angle does it have? Phi. This is the angle the voltage is having. So in other words, if you were to write down the time domain equation for this voltage, that would be equal to V cos of omega t plus phi, right? And in terms of phasor, what would be, how could you represent this voltage in terms of phasor? V with an angle of phi. Remember, phasor, the angle of phasor, you always get it from the cosine representation. Please make sure, don't do it in the sine representation or as a function of sine. All right, so what do you see here? The I. What is the angle for I in case of, so we're talking about resistors. What is the angle for I? The angle for I. So this is the current phasor. The red one that you see is the phasor for the current. What is the angle? Same angle, phi. So they are lying on the same line. So there is no phase difference between the current through a resistor and the voltage across the resistor. Don't confuse these voltages that we are talking about here. It's not the source voltage, remember. It's the voltage across that component. Make no mistake. It may be confusing to you, but make sure that you know this. These voltages that we are talking about now is the voltage across that component. It's not the supply voltage. Okay? Same here. The voltage that we are talking about is the voltage across that resistance. So for the simplest case, if you have just one resistor connected across an AC source, of course the source voltage becomes the voltage across that resistor. For example, in this case, in the simplest case, you might have something like this. You have an AC circuit and you just have one resistor connected to that. So of course, in this case, the voltage across the resistor becomes the source voltage because it's the only thing that is connected across the voltage source, right? So of course, obviously for this case, the voltage source voltage is the voltage across resistor. But consider this case. Let's change this circuit a little bit. Let's say we have a resistor and an inductor. So how about now? Is it the same? No, obviously it's not the same, right? So we have two voltage drops. So the voltage, so in this case, the voltage across the resistor or the voltage across the inductor would be very much different from the source voltage. Obviously, according to Kirchhoff's voltage law, when you add these two, the voltage across the resistor and the voltage across the inductor, that will be equal to the sum will be equal to the source voltage. So going back to this, these voltages that we are talking about now, they are voltages across that component. It's not the supply voltage. Okay? Good. I'm glad that you woke up before the class finished, so you might have to. Anyway, so this is the resistor. It's very easy. We understand this now. What about the inductor? Oh, sorry, that is the inductor. So this is the inductor. So this is the current. We started with current. It doesn't matter. So basically what you need to know is, in case of inductor, the voltage leads the current through it. Okay, the voltage leads the current through it, so that's what it's showing us. So if this is the current, the voltage is leading the current by 90 degrees. And in case of capacitor, the current is leading the voltage. So we set the voltage as reference, and we see, because it's just, you see, in case of inductor, we set the current as a reference, and then we find out the voltage is leading by 90 degrees. And in case of capacitor, we set the voltage across the current, voltage across the resistor, and we find out the current is leading it by 90 degrees. Why is that? Because it's the relationship, the original relationship. Remember, for the case of inductor, it's VL is equal to L di by dt. So this basically, because of that relationship, it's just customary to set that. It's no harm. Like even if you set this as a reference, only thing will happen, let's say if you set the current in this direction, so the voltage will be lagging by 90. So voltage will be somewhere like this. It's all about referencing. It's no big deal. It's all like custom. All right, so checkpoint. So far, single phase versus three-phase circuits, we didn't really cover three-phase that much, but obviously it will be covered in one of the later chapters. Time domain versus phasor domain for RLC circuits. All right, so use cos, this is the reference. Remember this one, okay? Cos of omega t, or use the signal in its cosine form as the reference. So this is very important, especially for your test and in your exam. Make no mistake. All right, to relate I to V in RLC series circuits, we have already covered that. And next, analyze RC, RL series, and parallel circuits. That's what we'll do now. We'll check these RC and RL circuits in series and parallel form. By check, I actually mean we'll see how the voltage and current relationships are for these configurations. All right, so before that, can you answer the following questions? The voltage Vt is equal to 12 cos of 60t. My hand is hurting. How about this? Will it work? Is it okay? So you have to cut this off when you edit the video. So we can continue until 11, right? So then you actually make it 1 hour. You're supposed to make it 1 hour, the video? So I'll continue until, because the class is until 11, and you can keep recording, then whatever you edit is up to you. Okay? All right. All right, so we have a voltage Vt which is equal to 12 cos of 60t. So 60, what is 60? Omega is the angular frequency. And 45 degrees obviously will become the angle of the phasor because it's already in cos form. Is applied to a 0.1 Henry inductor. So inductance of that inductor is 0.1 Henry. Find the steady state current through the inductor. Can you do it? Yes, you can. Because you're already familiar with the impedance of that inductor, you can right away find it out, J omega L. Okay? Or in polar form, that would be omega L with an angle of positive 90 degrees. So omega is what? 60. Thank you very much. And L is 0.1 Henry. And it's probably solved here. There you go. So XL, we have XL. What is XL? Reactance. Whenever we have just the imaginary part, which would obviously come from reactive or inductive elements, we call that reactance. It's an impedance, of course. Excuse me. The reactance is an impedance with the real part as 0. That's all it is. It's just an imaginary number. All right, series circuits. So very basic 3 series circuits. So the first one is just 1 R. So obviously in this case the voltage across R would be the source voltage. Same here, it's just 1 capacitor. And at the end we have a series circuit with capacitor and the resistor. The first case Z is what? R, just a real number. In the second case Z is XC, which is equal to J omega 1 over J omega C. Before I continue, I just wanted to make sure that you realize this. The impedance of a capacitor, or the reactance more accurately, the reactance of a capacitor, remember, XC is equal to 1 over J omega C, right? That we can actually write negative J over omega C. Why is that? How can we write this? No, you're right, actually. So you multiply J and J. Yes, he's right. So basically what I'm doing here is, if you multiply the denominator and the numerator with J, sorry. So the denominator becomes J squared, right? And what is J squared? Negative 1. So that's how it becomes negative j over omega c. All right, one thing you should notice in this slide is this is W. It's a typo. It's meant to be omega, okay? It's not W. Okay, for the third case, we have one resistor and one capacitor in series, and of course the Z is, the impedance would be R plus XC. It's a complex number because this is real part and this reactance is an imaginary part, which is a pure imaginary number. Okay, prove the following relationships. Can you prove this following? Let's try. Okay, what do we have here? We have a voltage source and we have a resistor and the capacitor. Basically, we have this one here. It's just a fancy representation. It looks nice so that you don't get bored. Because with this kind of figure, of course, you get bored. But when you see this kind of figure, you just wake up. Oh, nice. Okay. So what do we have here? We have R and we have C. And so let's try to find out how the voltages and the currents are related. Okay. All right. Let's start with what is common in this case. Can you tell me? One thing you should notice, the voltage across this resistor and the voltage across this capacitor, they are not same. Of course, that's going to be different, right? So what is common throughout this circuit? The current that is flowing through the branch. The current that is flowing through the loop is, of course, a single current, right? Okay, let's try to find out the current first. Okay, to find out the current, obviously, we need the impedance first. What can be the impedance? So Z is equal to R plus XC. That is equal to R plus, or rather minus J over omega C, right? So if we plot this in the complex plane, we'll get something like this, sort of like a vector. The length of the vector is in the imaginary axis negative 1 over omega C, and on the real axis we have it's R, right? So you see, we'll end up having an angle sort of negative, let's call it phi, negative phi. Is that okay? So in case of capacitor, the angle is going to be negative. So the total impedance angle is something negative. The amount of the angle is obviously, it will depend on the value of R and C. So it's going to be tan inverse the angle. Tan inverse what? Can you tell me? 1 over omega C as the numerator, and as the denominator it's R, right? That's how we can find out this angle, obviously. Okay? If you want to find out. But for now, we can see that it will be a negative angle. I can tell you now, actually, for the case of inductor, obviously, you're going to have a very similar situation, but with a positive angle. Because for the case of inductor, it's J omega L, right? You can write J here. And this is R. Because for the case of inductor, the imaginary part or the reactance is something positive. So you'll end up having a positive phi, right? Good. Very similar, complementary. One is sort of like opposite to the other one. Okay, so, okay, I'll give you a trick question now. If we just in case have R, L, and C, all three in one circuit, one series circuit, what kind of situation are you going to get? R is always in the real axis. For the case of capacitor, you're going to have something negative. Okay, remember all of this behaves like a vector, right? And you add up this vector to get the whole Z. And for the inductor, you're going to get a positive vector entirely lying with the y-axis, positive y-axis. So you see what's happening here, what's going to happen here? This vector and this vector is going to cancel each other. And the angles, again, the vector because of the phasor because of the inductor, because it's going to positive. So let's put it in the same plot. So you have here this phasor because of the capacitor. You'll have another phasor because of the inductor, which is j omega L. So if you try to add up, so we have three vectors now. Let's get rid of this. So notice we have three vectors now. Do you see? Three vectors lying in two axes basically. So what do you think would be the resultant? Can you make a guess? Of course, the first thing you'll notice that these reactances or the imaginary parts will cancel each other out. Not entirely though, depending on which one is bigger or which one is smaller. You will end up having a little reactance, either in the positive direction or in the negative direction, depending on their magnitudes. But there's a special circumstance, very specific circumstance that may happen is they cancel each other out very equally and the whole reactance becomes zero. That's possible as well. That's actually one, the phenomenon is called resonance. There's a very specific situation in electrical circuits. We'll be covering this resonance in later lectures. So you see what, it's a very nice relationship actually, and these reactances cancels each other out. So you might have the resultant reactance maybe here, something here. So you add these two and you get this angle of the resultant impedance, the total impedance. Is that okay? Clear until this point? All right, so let's go back to this series RC circuit. So we were talking about the series RC circuit. Let's redraw that. Get rid of the, and get rid of this. Let's put that back. So something like that. So we have phi, negative phi as an angle of the impedance. So this is that. Okay. So what would be the current through that single branch? So if the voltage is V, let's call it V with an angle of, let's say, 0. Okay, the current would be, sorry. So the current through the branch would be I is equal to V divided by Z, this total Z. Okay, and this Z has an angle of negative phi, something negative. We don't know. That will depend on the relative values of R and X and omega. Okay, so but we know that it's something negative. So let's write negative phi. So the resultant would be Im with an angle of positive phi. Okay, so obviously you can see the current will be leading the voltage with a certain angle because it's capacitive. If it's entirely capacitive, in other words, if there was just a capacitor, this lead angle would be 90 degrees, going back to capacitor voltage current relationship. So, but now there is because if there was just capacitor, this line would be here, and we would be having negative 90 degrees, and this angle would be 90 degrees. But because we have a resistive component, the angle is little more than 90 degrees. And so we have phi, which is more than negative 90 degrees. Okay, so the current through the branch will be leading the voltage by an angle of phi, and the phi will depend, the amount of phi will depend on the relative values of R and C. Okay, so now let's have a look at the voltages across each component. So for the resistor, what would be the phase of the voltage? So let's find out the VR would be equal to So which is the same I, because I is flowing, times R. I is flowing, the same I is flowing through the resistor and the capacitor. So basically we have just one current throughout the circuit. We don't have more than one current, right? So the voltage across the resistor will be IR. So I is equal to IM with an angle of phi, and we have just a real number. So basically IR with an angle of phi, because the current through the resistor, through this resistor, and the voltage across this resistor is in phase. Okay? And we already know that the voltage, the current through the resistor is leading this voltage, the source voltage, and that's why we get this. VR leads Vs by an angle of phi. Okay, what happens in case of capacitor? It's the very same way we can find out the capacitor. The voltage across the capacitor will be lagging the supply voltage by the same angle, actually this same angle, phi. Okay? And we already know this, the current. That's what we found out first. The current is leading Vs by an angle of this phi. Okay? Very simple. Let's move on. So these are the three relationships that we understood. Analysis of series RC circuit in time domain. Okay, so what we have here, Kirchhoff's voltage law, Vs equal to Vc plus VR. So basically Vs is equal to this voltage plus this voltage. So what we have here, let's have a look. So this is the current that we have, okay, through the branch. Remember, I took the current as the reference because that is something in unique, or just one value throughout the circuit. That's why we take the current as a reference. So that's all referencing these phase angles. It's all relative, right? So we say that this current has zero angle. That's why it starts from 0. Okay, so VR, obviously the voltage across the resistor is in phase with the current, and that's what you see. Of course it will be different magnitude, but it's in phase. It's going, starting at the same time, going to the peak at the same time, and coming back to 0 at the same time. All right, what about the source voltage? We know that source voltage, the current will be leading by an angle of phi. So in other words, the voltage will be lagging by an angle. So there it is. So in this case, it's written theta, just an arbitrary angle. So the voltage, source voltage, will be lagging this current by an angle of theta. So you see, whenever it's lagging, it looks like it has been shifted towards your right. Okay, so what about this Vc, which is the voltage across the capacitor? We know that the Vc is lagging the current through it. The voltage across the capacitor is lagging the current through it. In other words, the current through the capacitor is leading the voltage across, and this is, and by 90 degrees. So this is what you see. This is the current through the capacitor, and this Vc is the voltage across the capacitor, and this phase difference that you see here is 90 degrees. And another way to show it is, whenever the current goes to peak, the Vc is at its 0. Whenever Vt goes to peak, the current is at its 0. So which means the phase difference is 90 degrees. And you can see it here as well. All right. So development of the impedance triangle for the series RC circuit. This is the impedance triangle. So you have R, you have the XC, which is in the negative direction. So we covered this already. The resultant Z is going to have an angle of negative theta. And this is the resultant Z, which you get by sort of like vector addition. And here is the impedances or the reactances because of an inductance, and here is the reactance because of a capacitor. And we already know these things. Capacitor, for capacitor we have the reactance has a negative 90 degrees, and for the case of inductor, It has positive 90 degrees. Oh, I just changed my hand and it feels comfortable. All right, so of course the theta is equal to x tan inverse xc divided by r. Okay, what else do we have? Variation of impedance with frequency. Of course, if you have noticed by now, this is the time for you to notice that the impedance of an inductance and the impedance of a capacitor, for example, the impedance of an inductance, what is it? J omega L. So L is fixed, J is fixed, but omega may change. In other words, it actually depends on omega, the frequency of the source or the frequency of the AC supply that you are dealing with. Okay? So if omega goes up, the impedance goes up because it's multiplied with L. So what happens in case of capacitors? It's negative J over omega C. So whenever you have omega C at the denominator, so omega goes up, the impedance goes down. See, another complementary thing. So that's what we are talking about here. When frequency is changing, then this W is actually omega, which is the angular frequency, is also changing. Since the reactance here to the capacitor is 1 over j omega c, which is same as negative j over omega c, then xc is changing when frequency is changing. Okay. Since xc is the factor that introduces a phase angle in a series RC circuit, so the phase angle that we get in series RC circuit is because of the xc, right? In any AC circuit, the angle that we get in the impedance is because of the reactive elements. What are the reactive elements? The inductors and the capacitors. Okay, so here's the angle and there's the theta, tan inverse xc divided by r, which is equal to 1 over omega cr. So omega cr is equal to this one. Okay, as the frequency increases, xc becomes smaller and thus the phase angle decreases. We'll see how. Does that make sense? Because this is the resultant Z. For example, Z1, we had Z1 maybe for F1. And as we are increasing from F1 to F2, F2 to F3, this is how the reactances will change. As the frequency goes up, the reactances goes down. In other words, the magnitude of the reactance becomes smaller because it's 1 over j omega c. Okay? So the resultant impedance will change like this. Okay? So at first it was Z1, Z2, Z3. So here's a trick question for you. Hypothetically speaking, if you happen to have the frequency as infinite radians per second, what do you think is going to be the reactance from the capacitor? If you happen to have infinite omega, the value of omega is infinite, what do you think the reactance is going to have? The reactance is going to be 0. So in other words, the impedance is going to be 0. Impedance due to the capacitor is going to be 0. So what does that mean? Whenever you have a resistance or impedance 0, that means short circuit. That actually means it's short circuit. So capacitors act as a short circuit in high frequencies. So this is an approximation that is made in many electrical analysis, that in case of very high frequencies, capacitors are considered as a short circuit. So let me ask you this now. What do you think will happen in case of very high frequency? Okay, let me stick to the capacitor. What happens if the frequency is 0? In case of capacitor, what would be the impedance of a capacitor if the frequency is 0? If the frequency is 0, the impedance of a capacitor will be infinity. Whenever because it's 1 over j omega c. So you put omega equal to 0, 1 over 0 is equal to infinity. So in other words, the capacitor will behave like an open circuit whenever the frequency is 0. What has frequency 0? Do you know when do we have the frequency as 0 in case of power supplies? The DC. DC has a frequency 0. Okay, I can see many of you are feeling really sleepy. I mean, this should excite you. This one standing right here. You shouldn't feel sleepy because this is like a guard. This is watching you. Even though it's not phased towards you, but still you shouldn't sleep. Okay, so let me ask you this now. In case of inductors, we already know the impedance is j omega L, right? So in case of infinite omega, what do you think the value of the impedance is going to be? Impedance due to the inductor. Infinite. J omega L, infinite. So basically it's the opposite case that's going to happen in case of inductor. So in case of 0, infinite frequency, you are going to have infinite impedance, and in case of 0 or DC, in case of 0 frequency or DC, you are going to have short circuit. So you see, in case of DC, you had with capacitor you had open circuit, and with inductor you have short circuit. That's why we don't use capacitors or inductors in case of DC. It doesn't make much sense because it doesn't do anything. One acts as an open circuit, the other one acts as short circuit. All right, moving on. Impedance and phase angle for parallel RC circuit. Okay, first we had the series RC circuit. Now we have parallel RC circuit. Remember, in case of series RC circuit, we had one thing in common in both the cases, both R and C. There was one thing that was common to both of them, and that was the current that is flowing through it. And that's why we use that current as a reference whenever we drew that plot, time domain plot for the currents and voltages across this. But what do we have in common now? We don't have the current common anymore because there will be two different currents to these two branches, right? But still we have something in common now. What is that? Right. The voltage is common now, but we'll have different kinds. The same way, we can find out the relationships between the, so of course the voltage across the resistor or across the capacitor, now it's going to be the same voltage as the source voltage, but the current will be different. How do we find out the current? We just divide the voltage with the resistor and we get the currents to this branch, and we divide this voltage with this capacitor impedance and we get the current to this branch, and we can add up those currents to get the current through the main branch. Or another way would be to find out the equivalent impedance of the whole thing and divide this voltage with that equivalent resistance, equivalent impedance. That will give you the current to the main branch. Okay, let's see what we're going to do. Sorry. So here it is, and so this is the series AC circuit, and this is the parallel AC circuit. Okay. The currents IS, IR, and IC. IS is the, I think it refers to the total current. Okay, so Kirchhoff's voltage law. In this case, Kirchhoff's law, Vs equal to Vr, which is equal to Vc, same voltage everywhere. So total current, which is I total, would be equal to IC plus IR, and these are vector signs, refers to the, it actually implies that these are phasors. The currents are phasors because it's AC. Everything is phasor now. Okay, so we know that the current this current is going to be in phase with this voltage, right? Remember? Because this current is going to be, this current, IR, is simply Vs divided by R. This current IR is equal to Vs divided by R, because this is Vs from this point to this point. The whole voltage across R is Vs now. So the IR is going to be equal to Vs divided by R. And R is Vs, okay, let's say that is phasor. But R is not a phasor. It is phasor, but with 0 angle. So that's not going to change the angle, which means IR will be in phase with the Vs. Okay? So let's put it in 0 angle. So what about IC? Remember, the current in the capacitor leads the voltage across it by 90 degrees. So we know that this is the voltage across it, because IR and Vs are in the same phase. So since IR is here, Vs is here as well, lying with the x-axis. So obviously the current through the capacitor is going to lead the Vs by 90 degrees. So it lies vertically upwards, the IC, the current through the capacitor. Okay, so this would be the resultant angle for the total current, which is this total current. You add these two because the total current is IC plus IR. Does that make sense? Is that okay? All right. Moving on. IR is in phase with Vs, so and VR is equal to Vc. So IR, there you go. We have the Vs here, and we have the IR, which is indicated in with the blue line, and they are in phase. They're lying together. Then we have the IC, which is leading Vs by 90 degrees. We know at the beginning of this lecture that the current through the capacitor leads the voltage across it by an angle of 90 degrees. Okay, that's how you get I total. You add these two vectors, you get I total. All right, so let's find the I total if C is equal to 10 millifarad, R is equal to 20 ohms, Vs is this, volt for the following circuit. So this is the circuit that is given, and we are supposed to find out the I total. Can we do it? Yes. It's not too difficult. And the easiest way would be to do it in phasor domain. So we can write down the phasor for the source voltage. What would be the phasor for the source voltage? The phasor for the source voltage. Negative 45 degrees angle, is it? I think so, because we have to convert this sign to cos. So that's going to be 20t plus 45 minus 90, which will be negative 45 degrees, and the amplitude remains same. So 10 with an angle, amplitude 10 with an angle of negative 45 degrees. So there you go. The first thing is done. Then we have to find out the phasor for this one, and this is easy. It remains the same. But for this one, it's negative j over omega c. So what is omega? Can you tell me the trickiest part? What? 20. Perfect. It's given here. Omega is 20. Okay? So you find out the reactance for C, which is negative j over omega c. And from there on, you can find out IC, and you can find out IR. IC, IR. Okay? And then, so these this voltages, and this is XC. And once you find out IC and IR, you add them up, and you get I total. You can add them up graphically, or can you add them up in polar form? You can, only if you use a calculator. But if you want to add it manually, obviously you have to convert the polar form into rectangular form. Yes. Then you add them up, and then you take it back to polar form. All right, so there are some extra notes, self-study. You can do it at your own time. If the current through the inductor is Zero. So this is basically a recap of whatever we have covered until now. Then the voltage across the inductor is Vt L di by dt, and so on and so forth. So we are familiar with this relationship already. We can see that the voltage is leading the current by 90 degrees from here. Okay, so that's how we get this 90 degrees associated with the reactance of the inductor. All right, phasor relationship for capacitors. We already covered this. The voltage current relationship through the current through the capacitor I and the voltage across the capacitor V. And this gives us this relationship. The impedance for a capacitor is 1 over j omega c or negative j over omega c. Phasor relationship for capacitors. So if a voltage through a capacitor or is actually across a capacitor, it's not through, okay? So this is the voltage across a capacitor. In phasor form is Vm with an angle of phi. Then the current flow through it is this. We already covered this, and that's how you get the impedance or the reactance of a capacitor, which is 1 over j omega c or negative j over omega c. And this could be the relationship. If the voltage is here, the current through the capacitor will be leading the voltage by 90 degrees. Okay? Complex quantity, we covered this in the last lecture. Example, exponential form. So we'll talk a little bit about exponential form. We actually did not do this in the last lecture. The last lecture, we only talked about polar form. In the last two lectures, rather, polar form and rectangular form. But there's another form to represent this phasor, which we are not going to be using that much, and this is called exponential form. Okay? And this exponential form actually comes from Euler identity. There's something called Euler identity that gives us this relationship. Okay? I'll show you what Euler identity is just very quickly. This is the relationship that we get using Euler identity. Okay, so this is exponential to the power j phi, which is equal to cos of phi plus j sine of phi. This is a relationship, and this relationship is called Euler identity. Okay, so let's go back to the presentation slide. All right, so this is the thing we get. So it looks familiar to the Euler identity, right? So this is actually Euler identity. This would be equal to e to the power plus minus j phi of omega t plus 135 degrees. Okay, so this is the answer. If you want to, so the left side on the Euler identity, which is e to the power something, is called the exponential form. So in exponential form, so using Euler identity, we can represent this as in an exponential form. So in an exponential form, it would be, again, e to the power plus minus j of omega t plus 135 degrees. Remember, you cannot use degrees. You have to use radians in Euler identity. The angle as the power of the exponential, you must use radians, not degrees. And this would be the answer. So if we convert 135 degrees into radians, this is 3 pi by 4, and there you go. 5 is the magnitude, 5 e to the power 3 pi by 4 j, which is approximately equal to 5 e to the power 2.36 j. All right, so express negative 1 plus 5j in exponential form. If you convert this using Euler identity to exponential form, you'll get this. This is the answer. Okay. So another way to do Euler identity is basically if you convert this, so the easiest or the direct way to convert a phasor, whether it's in a rectangular form or in polar form, to Euler identity is to take the angle. So this one, for example, is given in rectangular form, right? So all you have to do is convert this into polar form and take the angle, and that angle you just put it here as a multiplicand with j, and you put it at e to the power j of that angle, and this is the magnitude of that polar representation, and that's it. Impedance Z, we have talked about this. What else is left? So we have covered all this relationship. DC inductor acts as a short circuit, capacitor acts as open circuit. AC very high frequency, we talked about these things. Phasor relationship for circuit elements, we have covered these circuit elements. Passive elements, resistor, inductor, and capacitor transform the voltage current relationship of those elements in time domain into frequency domain. Okay, so impedance continuous, we have covered these, right? Z can be in polar form, can be expressed in polar form. So this is the impedance in rectangular form. Obviously, anything that is given to you as rectangular form can be expressed in polar form, and vice versa. If I give it to you in polar form, of course, you can represent it in rectangular form. Now you can do something more actually. You can represent these things into exponential form. And the easiest way to do the exponential form is take it in polar form and use the magnitude, same magnitude, but instead of the angle, you use e to the power j phi, plus minus j phi. That's it. Okay, so admittance. What is admittance? Admittance is the inverse of impedance, so 1 over z, simply. It's called admittance. So let me ask you this. What is conductance? Can you tell me what is conductance? Conductance is 1 over r. If you have an r and if you invert it, that becomes, we call that conductance. Then we have reactance, right? What is reactance? The imaginary part. This part, it's not here. So these are reactances, pure reactances, the imaginary part. So 1 over reactance is, what is 1 over reactance? Admittance. Sorry, 1 over impedance is admittance. 1 over reactance is, we'll see in a bit, in those later slides. All right, so admittance can be expressed rectangular or polar form. We know that already. G is the real. So this is the admittance, okay, which is 1 over z. So z is a complex number. 1 over z is a complex number as well, plain and simple, which means that it's going to have real part and imaginary part. So this is okay. So this is the thing that I was about to tell you. Susceptance. 1 over reactance is called susceptance. 1 over reactance is susceptance. 1 over impedance is what? Admittance. 1 over R is conductance, and 1 over X, C or L, whatever that is called susceptance. All right, parallel RC circuit. So impedance combinations in case of parallel, you're already familiar with this, I'm sure. You have, did you cover parallel resistance combinations in any of the previous courses, or maybe in high school? How do you add up resistances if they are connected in parallel? You add up the conductances. You add the conductances and then you invert. I'll show you how. I'm sure you all know this. It's a matter of reminding you. So you have, let's say, two resistances in parallel, R1 and R2. So we want to find out the equivalent resistance of these two resistance which are connected in parallel. How do you find out? You, as I said, you add up the, what are these? These are conductances. 1 over R are the conductance. So you add the conductances, then you invert it. Invert it means 1 over. That gives you R equivalent. Remember? In case of series connections, of course, it's very, very easy. You just add them up. But it becomes a bit trickier whenever you have the parallel combination. So there it is. There you go. So whenever you have series, you just add them up. This is the summation from 1 to n, whatever the n is. N is 3 if you have 3 impedances. N is 4 if you have 4 impedances in series. So you just add them up. What happens if you have parallel? There you go. Same principle. Whatever you did with resistances, you do the same thing with impedances as well. So you basically add the, what are these? Admittance, right? Inverse of the impedances. So you add the admittances, all the admittances. So because these are given in impedance form, so you invert them to get the admittance, you add them up, then you invert the whole summation. And you get the parallel combination of these impedances. All right, let's go back. In case of series, resistance capacitor, we did this already. So it's here, it's an example that's showing the parallel series combination of ZR, ZL, and ZC. So for R, you have these. So basically, you are adding up 3 impedances. And this is how you do it. For ZL, you replace with j omega L. And for ZC, you replace with 1 over j omega C, and you work it out. So this is the same Z equivalent in what? Exponential form. Okay? So that exponential form, this is Euler identity. Remember Euler identity? The exponential form can be represented as this Euler identity. So from here on, you get, so there are various ways. So this is one of the ways you can actually find out impedance, but another way would be to just directly add them in rectangular form. You don't really have to resort to this method all the time. So you can avoid coming to this Euler identity. Same with parallel combinations, very easy. So here we can see the parallel combination of, can you guess what are these? Parallel combination of what? This one we're trying to do a parallel combination of something. What is it? From the equation, can you identify? It says it on the title. There's a resistor and a capacitor and an inductor in parallel. So that's how you do it, right? When 2 impedances connected in parallel, so this is what it is. Very simple. So impedance and combinations. We'll not be covering this in this chapter, but when we reach 3-phase circuit in, I think next week or the week after, we'll be covering these 2 different types of connections. Basically, these kind of connections start making sense when you start dealing with 3-phase circuits. All right, RC circuit, resistance, R, capacitor C, these components, series and parallel arrangement. So only solve problem with the same frequency. Of course, throughout this course, we will be considering single frequency unless otherwise stated, using phasor to solve the problem. All right, so here are some recaps that you can go through in your own time. Please do go through this slide, and also the associated module is already uploaded on the website. So please do your homework. All right, so development of impedance triangle. We know these already. Impedance in series, RC circuit. So this is R and C with the series combination. Analysis, recap series and parallel RC circuits. So these are just the recaps. Conversion from parallel to series form. Okay, so this is something that has not been covered. So whenever you have a parallel circuit, let's say you have a parallel circuit, Z1 and Z2 in parallel. So you can find out the Z equivalent, right? If I give you a parallel circuit with Z1 and Z2, of course you can find out the equivalent circuit. How do you find out? You add up the admittances and you invert that. Parallel combination. Okay, so what is the result? In case of phasor, so Z1 and Z2 are phasors, so you add up the impedance admittances and invert them. At the end, you are going to get a phasor, which is in rectangular form, that is going to be a complex number, right? Plain and simple. It's a complex number, or if you represent it in polar form, that's going to be in polar form. So if you have the equivalent impedance in complex form, that means that's going to have a real part and an imaginary part, right? So once you have a number, complex number, which has a real part, that real part you can represent as a resistor. And that imaginary part of that combination or that equivalent impedance is going to be a reactive element. Depending on the sign, that can be represented as an inductor or a capacitor. If it's a positive complex number or imaginary part, you can represent that as an inductor. If the imaginary part happens to be negative, that's going to be a capacitive reactive element. And that's what it's talking about. Whenever we have a parallel circuit, there's a way to represent that same parallel circuit as a series circuit. So that is going to be an equivalent. Conversion from parallel to series form, draw the circuit in both series plus parallel arrangement. In series arrangement, get the phasor diagram of impedance using Kirchhoff's law to find the relationship Z is equal to Vs divided by Is. Okay, impedance triangle for this equivalent. Let's go back. Let's see if we missed anything. Okay, convert. Every parallel RC circuit at any given frequency, there's an equivalent series RC circuit. Of course, two circuits are equivalent when they both present the equal impedance, equal phase angle. Thus, when we need to know impedance Z and phase angle theta, then construct an impedance triangle using the impedance Z and phase angle theta, draw the circuit in both series and parallel, and so on and so forth. So this is exactly what I just told you. And that's the end of this presentation. Let's have a look. What did we actually have? Let's go back to the... So this is the things that are expected as the learning outcomes from this lecture or from this chapter. The first one was you guys are expected to be familiar with single phase AC circuit. And the second was you should have gained the understanding of the behavior of various AC components by now. The components are basically the impedance of R, L, and C in a single phase circuit. And the third expected outcome was you guys should have gained a clear understanding of the relative phases within the single phase AC circuit. And the last one was the expected outcome. You guys should have be able to analyze a single phase circuit using phasor representatives. Right? So pretty much all of these outcomes I think have been covered in this lecture. Let me ask you a few questions. So basically to sort of get a feedback based on these expected outcomes. Okay, let me ask you the first question. What do you think? What do you mean by single phase AC circuit? Anyone? Maybe you. Just briefly tell me what is single phase AC circuit?
single phase AC circuit is the electrical circuit involving alternation current. The term of the single phase is means that it indicates the only one voltage across the circuit, whereas the two or the three phase circuit means there is more than one voltage in the circuit apply.
All right, thank you very much. What's your name?
Nurul Alia.
All right, Nurul Alia, thank you very much. Yeah, so that's something I was expecting, so that you already know what is single phase. So basically, it's whatever we have in the household environment as a power supply. Okay, let me ask you another question regarding the inductor voltage and current relationship. Does the voltage across the inductor leads the current or lags the current? Can anyone just briefly tell me about that? The inductor voltage leads the current or lags the current, okay? Tell me your name first and then you can answer.
Okay, my name is Mohammad. Okay, the inductance, the voltage across the inductance leads the current through the it. And this can be seen from the voltage current relationship, which is Vt is equal to L di dt, which means voltage is equal to the rate of change of current and divided by inductance by L. Okay.
Right?
Yeah.
Okay, excellent. Thank you very much. So yeah, I can see that at least some of you have the understanding of the voltage and current relationship within an inductor. That's great. All right, so okay, let me ask you this. What about like the capacitors? Voltage and current across a capacitor, can anyone tell me? Like, it's a very similar question, but in case of capacitor, what can we expect? Anyone? Okay. Tell me your name and then you can answer the question.
My name is Afiq Amirullah. The answer is the current through a capacitor is equal to the rate of change of the voltage across it multiply by the capacitance value, or in other words, IT is equal to C time by dV by dt over dt.
All right. So it's proportional to the rate of change of voltage. And the resultant is the current leads that's what we saw. The currents lead the voltage across it by an amount of 90 degrees, right? That's great. Thank you very much. What was your name? All right. Afiq, thank you very much. All right. So also we talked about the parallel combinations and series combinations. Let's say in case of parallel combination, okay, we saw a problem, right? We had to find out the current through the main branch of a parallel circuit. So of course, in the parallel circuit, there were two currents. So how can we find out if you can remember briefly how we found out the current through the main branch of that parallel circuit? Can anyone tell me just briefly? All right. We have someone from at the back. Okay, tell me your name and then you can answer me the question.
Okay, hi. I am Amirul. Okay. Okay, it's very much same like DC circuit. Okay, in AC circuit, find first thing first. We have to find out the equivalent impedance. Of all the component in the domain phasor domain. Okay. Then we the way to find out the equivalent impedance is how we look on the all component connect in series, parallel, etc. Okay. Then if we divide the voltage source with the equivalent impedance in the phasor domain, then we get the result, the total current in the phasor domain. Okay, that's all.
All right.
Thank you.
Answer. Thank you very much, Amirul. Thank you very much. So that's great. So I guess so far so good. I'm a bit satisfied from the feedback that I'm getting from you guys. So now, if you guys have any question, feel free to ask me. If you have any question regarding this course, regarding this, sorry, not course, the lecture, feel free to ask me now. Any question? Anyone? Yep. Go ahead.
I want to ask.
Please tell me your name first and then ask me the question.
Alright, my name is Sharifa Mariam. I'd like to ask about the example about exponential form. Like the calculation, the sign, we have to change to cos, right? This one. This one about the slide. You have to change about cos. And
Okay,
then
let me go. Thank you very much. Let me go back to the slide so that I can ask you the question nicely. Okay, so I think your question is based on this slide, right? And what exactly is your question in the exponential form?
if we change the 105 to radian, we get the answer already 3/4.
Yes, that's what you get, yeah.
Which means like we just ignore the sign and cos.
Sine and cos. Okay, so this comes from the Euler identity. Sorry, what was your question? Sine of the
Yeah, like do we just ignore cos and sine, or do we have to change the sign to cos?
No, you don't do anything. It comes from the Euler identity. Remember the Euler identity that I was telling you about? So this is the relationship that I was talking about. This relationship is called Euler identity. You have to remember this. How do we get this? Of course, you can dig it up. You can look it up. But for now, know that this is the relationship that we were talking about. And from this relationship, we get this kind of representation. And this kind of representation, we call this exponential representation. Okay? And of course, this is part of your module. This is in the module. Did you get your question? Okay. That's great. Thank you very much. Any other question? Pavin, okay.
Well, in the middle of the lecture, you did mention something about resonance. I couldn't actually grasp the concept. Could you explain about that?
All right. Thank you very much, Pavin. Very nice question. I'm glad that you actually took a note of that point. So resonance, yeah, I did mention about resonance, but I didn't really elaborate on that because it's not part of this lecture, but I'll still, since you are interested, I'll still briefly cover that. The resonance is a very specific phenomenon that can happen or that can be created, sometimes it's deliberately created, in an electrical circuit. Remember the phasors that we talked about. If you happen to have three components, let's say, in your series LRC circuit. So you have all L, you have R, and you have C. So the impedances, the phasors will sort of look like this. So this is because of the R, this phasor you get. This is because it's in the negative direction. This could be because of the capacitor. That can be negative J over omega C. And towards vertically up, you'll get the reactive components because of the inductor, right? So see the situation here. You have three vectors and you have to add them up to find the equivalent resistance or the equivalent impedance. So in a very specific situation, this might happen that these two impedances, these two reactances, cancel each other out because of the frequency is such that these two actually becomes equal, because you notice the dependence of these reactances with the frequency. If the frequency goes up, this one goes up. If the frequency goes up, this one goes down, the magnitude. So there may be a certain frequency. You can calculate that frequency, that particular frequency. At certain frequency, what's going to happen is if you keep changing the frequency, at a certain frequency, we call that resonance frequency actually. At that frequency, these two reactances will cancel each other out. As a result, the equivalent impedance is going to be purely resistive. And that's a very interesting phenomenon. And actually, we use this in some circuits, and this is called resonance. Is that okay, Pavin? All right, thanks. Anyone else? All right, great. First tell me your name and then you can ask me.
My name is Mohammad Nazmi. I have one question about the phasor angle. Is it we need to change from sine to cos to find the phasor angle, or just remain and just use positive, negative?
Okay. All right, great question. Thank you very much, because I can see the source of confusion. Yeah, to know the phasor of any AC signal, you have to, because the phasor of the components we know already. There is no confusion about that. But to know the phasor of any AC signal, you have to convert that AC signal or represent that as an AC signal as a function of cos, not as a function of sine. That is the standard. But believe me, if you represent everything as a function of sine, the calculation will be accurate and everything. There is no problem with that. But the standard that I realized later is to convert everything to a cos, function of cos, and take the angle of that. Whatever angle you have, or whatever phase you have as a function of cos, that should be the angle of your phasor. Okay? All right, so anyone else wants to ask me any question? Great, I think we're done for today. All right, thank you very much, everyone. And best of luck with your test on Sunday night. Thanks.